Okay, thank you very much. So this is a joint work with Thomas Ehrhard and Claudia Faggian here in Paris. And it is about interconnecting two different domains. On one side, Bayesian inference on graphical models, and on the other side, lambda-calculus and term rewriting. So let me just give a short recap of the variable elimination algorithm, which is one of the most basic algorithms for inference in Bayesian graphical models. So we have a Bayesian network that can be represented as a directed graph, as in these examples. The nodes of the graph represent random variables. So in this talk, the variables will be all Booleans, meaning that the possible sampled values will be 2, either true or false. But of course, we can trivially generalize to any finite or countable random variable. And the edges of the graph describe conditional dependencies. So a Bayesian network gives access to stochastic matrices describing these dependencies. So for example, here I write with the P of D, a stochastic matrices describing the dependencies of the variable D from the variable B and C. So here we are saying that if the sprinkler is on and it is raining, it is a high probability that my grass will be wet and a low probability that it will be not. Now, the question solved by the variable elimination algorithm is fix a subset of variables or a subset of nodes of the graph, and we wanted to compute the joint distribution of the variables associated to these nodes. So, for example, if you wanted to describe the joint distribution of D and E, a trivial way of doing that, a naive way of doing that, is to multiply all stochastic matrices associated to the different nodes of the graph, and then to sum out the variable that we are not interested in. So here we have this multiplication, and here we are summing out A, B, C, that are the three variables we are not interested in. And this gives a vector giving the joint distribution of D of A. So that's simple, nice, but it's a bit inefficient because you can check that it requires about 2 to the power of 5 basic operations. So it is essentially exponential in the number of the nodes of the graph. So it's quite unfeasible for real-world models. And variable elimination, improve it by factorizing this algebraic expression by taking profit of the conditional of the dependencies and the independencies of the variables as they are modeled by the graph structure. So, for example, so formally the algorithm is written here. It takes as an input a Bayesian network, a list of variables that we wanted to eliminate. So in our example, we wanted to eliminate A, B, C. So we give it in a specific order. So we wanted to eliminate the first A, then B, and the C. And then it run this loop that takes a variable. It makes the products of all the factors that are, of all the matrices that are involved in the variable, and it sum out the variable that we wanted to eliminate. So in the case of the elimination of A, B, C, morally it gives this expression, which is a factorized version of the previous one. So here we are, okay, this is not, oh la la. Sorry. Okay, so here we have we have factorized the sum over A with the three matrices that are involved in A. We put this factor in memory, and then we compute the sum over B. We put it in memory, and then we compute the sum over C. So we get the original vector giving the joint distribution of D of A. Of D and E. And what we have gained now is that you can check that by using this trick of memorization of the intermediate factors in the memory, we can have a computation which is about 2 to the power of 3 operations. So we can gain a bit. Of course, not all orders are efficient in the same way. So there are some that are as inefficient as the naive ways. As for example, if you take a CBA, you will get 2 to the power of 5 basic operation. Okay. Great. What is happening? Okay. Okay. So what are the questions that we wanted to study in this very classical algorithm? We wanted to understand a bit better the nature of the factors that are appearing in the algorithm. So at the beginning, the factors are just stochastic matrices, but as the algorithm is run, the intermediate factors appearing are a bit more complex than just stochastic matrices. They cannot be precisely defined as stochastic matrices. And usually in the literature, they are just described as vectors or matrices of real numbers, while they have a bit of structure in it. And we would like to unlight it. And the second question that we wanted to express is to try to describe this algorithm as a kind of a rewriting over some syntax that describe this factorization structure. So this idea of having a Bayesian network and some nodes that are put together in order to factorize the algebraic expression describing the joint distribution that we want to compute. And in order to answer to these two questions, we use two tools, so lambda-calculus and linear typing. So let us give a bit some hints on it. So first of all, we can remark that the Bayesian network in the example, together with the question of computing the joint distribution of D of A, can be described by this term here. So here, okay, it is a let term, but it can be just a syntactic sugar for a lambda term, if you wish. And so here we are saying that actually this let constructor corresponded to the sample constructor used in the previous talk. So it's better to call it sample. So we are sampling a value from P of A, from the variable A, and then we take this the sample value, we give it to P of B, P of C, we sample a value of B, a sample of C, and so on and so forth. And at the end of this stack of samples, we return the two variables that we wanted to observe. Okay, this term here, if you interpret it in some categorical semantics, in some denotational model, like relational semantics or probabilistic Corner spaces, what you get is exactly the algebraic expression that I give you at the beginning of the talk, the naive one that consists in making the multiplication of the 5 stochastic matrices PA, PB, PC, PD, PE, and then summing out the 3 variables, which is inefficient. The point is that a very similar syntax can express the factorization of this basic algebraic expression. So if you consider the one that improved given by the elimination of first A, then B, then C, well, it can be expressed by these other. So if you look at a bit in the detail, you can see that the first factor, the one that sum out A, corresponds to this sub-expression. So the idea is that the factorization expression corresponds to the nesting of the let expression in the syntax of lambda calculus. And eliminating a variable corresponds to making a variable local. So here we have this sub-expression here of the term is describing the pink factor here. And you see that the variable A here, xa, is actually local to this sub-expression and does not appear outside. It cannot be used outside. And so on and so forth. This sub-expression here, violet, correspond to the second factor here. And you see that the variable xb is local to the subexpression. So this is a general, this is a slogan, but it can be applied to any run, any factorization given by the variable elimination algorithm. We can apply it, but in order to do that, we have to introduce high order variables. So not just ground variable suffices if we wanted to represent in that way the factorization given by the variable elimination algorithm. For example, here we have a bit more involved example. Here we have a Bayesian network. And if we are interested to describe the factor obtained by eliminating the variable P1 here, so we have to describe in some sense a matrix that takes P1, P2, P5, P3 and sum out the variable on 1. We will get the problem of this representation is that here we have some output, so the output of P3 and the output of P5 and the output of P2. But the problem is that the output of P5 depend from an input, P4, that actually is depending from another output of the same factor. So we have a kind of cyclic dependence. And in order to represent it in our syntax of let terms, we need to introduce a variable f, which is actually a function, so a functional variable, which describes the possibility of computing P5 once we know the variable that still we do not know, which is x4, which depends from the other variable that is given by this factor that is x3. So this expression here, which is a perfectly well-defined expression in lambda calculus, if you interpret it in a denotational semantics, give rise to exactly the same algebraic expression that you have by applying the variable elimination algorithm and eliminating the variable P1 on that Bayesian network. So in general, here you have the syntax of the terms that we need in order to represent any factorization. So we have tuples of ground variables. So we have let expressions, and then so that is local definitions of tuples given by some expression. The expression can be either a stochastic matrices applied to a tuple of ground variables, or an application of a functional variables to a tuple of ground variables, first order functions, tuples of expressions, and again, a local definition of an expression in an expression. What you can prove is that if you have any factorization on the Bayesian network, well, it can be represented by a closed term in this grammar. And if you take a closed term in this grammar, you can associate it a factorization in a Bayesian network. So this is the first result, but this is not enough for us. We want not just to represent the factorization as a let expression. We want also to describe the run of the variable elimination algorithm as a kind of let rewriting. And so the question are, what are the rules that we need to introduce in order to go from a basic let expression like that one, describing the naive computation of the joint distribution, to an expression like this one, describing a run of the variable elimination algorithm. And actually, our surprise was that the rules that we need are just 4, and very simple ones. The standard one are just a let floating rewriting that is quite well known in the community of compilation of functional programming. So here you have the commutation of two lets that does not depend each other. So it's quite a simple one. Here we have the commutation, the possibility of commuting a let that depends from some variables defined before by introducing the this functional dependence here. And here we have the possibility of putting together two let definitions, so to making factors being increasing factors. And here we have the rule eliminating a variable that is not used in the in expression. So this is the one that is implementing the elimination of the variables one. This is used just locally in M and not in Q. So these 4 rules are enough in order to rewrite any representation of a Bayesian graph into a representation of any factorization of its algebraic expression. And this is given by this theorem. So you take a factorization of a Bayesian network, you apply the variable elimination in order to get a further factorization that eliminates the variable we are focusing on. And you can prove that if you take a let term that represents this factorization, by using these 4 reduction rules, you get a let term representing the factorization given by the variable elimination algorithm. And this theorem is constructive in the sense that we give a reduction strategy that produces from L this L prime. Okay. Great. So a benefit of this work, what we learn from it, for my personal opinion, is the presence of types. So now these terms are completely well typed, and they are well typed by this system here, which is a linear system. Okay, I don't want to enter too much in the details. We are using linear functions because what we duplicate in a term is not stochastic matrices, but are sample values of stochastic matrices. So for that reason, the duplication, so for that reason, this let expression can be defined as linear functions. But the most important thing is that you can, by using standard isomorphism in linear logic, you can rewrite the type that we use to type all the terms we are using in order to represent this factorization by this grammar. So we can this typing system can be reduced to this one, and this one is saying us that the factors that are produced by the variable elimination algorithm are either the tensor unit that is just a value, or are finite coproducts of factors, or are finite products of factors. Now, if you take just the tensor unit that represents just a value, something that is not probabilistic, if you take the finite coproducts of a value, you get what corresponds semantically to the probabilistic distribution, finite probabilistic distribution. If you take finite products of finite coproducts, that corresponds to stochastic matrices. 1 minute, and then you start, and until here we have something that is well known. Stochastic matrices are well known, but then what you get by running the variable elimination algorithm, you can have probabilistic distribution of stochastic matrices of stochastic matrices, and so on and so forth. So the original question we started with was what is the nature of the factor produced by the variable elimination algorithm, and our answer is in this hierarchy. It's a kind of stochastic matrices of stochastic matrices of stochastic matrices, and this way of representing the algorithm give a precise type to any of such factors. And I can stop here. So thank you.
Awesome. Thank you, Michele.